we have the sword of Damocles hanging over our head, impending disaster for all of us, because we know that quantum computers will break most of the forms of encryption that exist today on the internet. Once they get to 10,000 or more sustainable qubits, they're likely to overpower what we have, so we have to move to a post-quantum form of encryption. One of the most popular is fully homomorphic encryption, invented or first implemented at Stanford University by Craig Gentry. Well, when you press the enter key on your computer and enter a password, your data goes to the cloud, and now the cloud has your key. It can decrypt the data that you sent, so it performs computation, re-encrypts it, and sends it back to you. It's exposed as plain text data while that computation is going on, and therefore is subject to hacking and all sorts of other risks. But fully homomorphic encryption is very different. There, you encrypt the data, your data, with a very secure form of encryption, believed to be quantum proof. You send it to the cloud in encrypted form, and then all computation occurs on the data while it remains encrypted. Sounds like magic, yes? So it's then returned to you, still encrypted. No one else had a key. No one else was ever able to see your plain text data, and only you have the key. So it's not a surprise that the US Department of Defense refers to this as the holy grail of encryption. Well, it makes possible much more than just secure AI. It means that we have a future for data sharing. If you own a valuable database and you give it to someone else in trade for money, you run the risk that they'll steal it. But if you keep it encrypted with fully homomorphic encryption, then they never see the data, and you can rent it again and again. So information sharing now becomes a mega business because you can rent out your data in the future and charge them to decrypt the results of their queries every time they ask you to, so you can give them a key. In addition, GDPR, data processing regulations, fines in Europe alone over 6 billion euros so far. But with fully homomorphic encryption, your data is never in a data center. It can never be stolen. You can never be fined, so you are relieved of any liability. Well, the application to artificial intelligence is interesting as well, because we need to protect the users of large language models, and we need to protect the owners of those large language models. How do we do that? We create an encrypted query, and the open source model can be queried. Now, most major companies like Apple and Amazon don't want their employees interacting with an open source model because they give away too much information in the course of doing that. But if your queries are encrypted, and if the result is encrypted, and if all intermediate results are encrypted with a secure form of encryption, then there is no risk that anyone can discover your query, the result of your query, and suddenly now you are protected. And in addition, for the owner of the fine-tuned data in the model, so companies add to a foundation model their own proprietary information, you need not encrypt the open source model. You only encrypt the fine-tuned data, and then you do encrypted queries to both the encrypted data and the open source model. You combine them, you have your result. Everything that's proprietary remains encrypted. The result is encrypted, and now no one can rip off your model. Your model is protected from theft. Well, hey, this really sounds great. Why doesn't everybody use this? There is a minor catch here. That is, it is computationally very complex. So complex, in fact, that 4 bytes of data has to be in the encrypting process turned into 1.7 megabytes. And for computation, every CPU operation generates more than 12 million CPU operations. Plus there's overhead, something called bootstrapping. So the net result is that something which requires 1 second to compute on plain text data now requires about 11 days to compute on encrypted data. not very practical. In addition, traditional von Neumann computers cannot handle the data movement problem. So a von Neumann computer takes data from memory, computes on it, puts it back in memory, and so it's continuously in a memory bottleneck. It has contention, it doesn't scale. And so if you take, for example, this data from an Intel Xeon, you find that adding more cores along the horizontal axis does in fact improve the performance up to 4 or 5 cores, and then it actually decreases. It's what's called Amdahl's law. The synchronization process eats up more computation cycles than you gain in terms of the additional cores. So, what's required? As you've heard in many other presentations, a new architecture is required. You need to do things very differently. You need to get away from von Neumann architectures. But you need to start with software. And that, in fact, is what Cornami did. Cornami is named for a tsunami of cores, that is, multiple cores per chip. And the TrueStream compiler takes any arbitrary application and vectorizes it, divides it into parallel streams. About 7 years of the company was spent optimizing that, and then ultimately it was determined that the only way you could sell it is if you did a chip to implement it. So remember, this is the opposite of most of the companies you talk to. They develop innovative hardware architectures, and then they try to figure out how to program them. In this case, 7 years was spent optimizing the software, the programming, and the compiler, and then that was implemented into hardware. Well, it turns out that parallelism is what generates most of the performance gain and the power efficiency. NVIDIA, for example, uses single instruction multiple data to accelerate its processing. But in fact, Patterson and Hennessy have identified 55 different forms of parallelism, most of which are not utilized today. In the Cornami architecture, you start with the TrueStream compiler, which gives you the parallel data streams, and then you apply them to a sea of cores, thousands of cores per chip, and those can be reconfigured in software and formed into various processing modules, and then that can be scaled. If you want to double the performance, you double the number of cores. So twice the number of chips, twice the number of servers, all the way up to 64 million cores. Well, the other thing is that you want to get a hardware architecture that takes the shape of the software that you're trying to compute. To take an example, for example, something that NVIDIA does very well, single instruction multiple data. This is an image processing application, SegNet basic layer 7. And so you have large parallel processing in a portion of the design, but every cycle you're going back to memory again and again. If you do that with a data flow architecture where everything flows continuously, the difference is with the NVIDIA type architecture, you get one output every 16 million cycles. With the data flow, you get one result every cycle, so it's approximately 16 million times as fast, a big gain in performance. And there are hundreds of other ways, well, there are up to 55 other ways. A good example is pipelining. If you have something that requires 100 clock cycles and you load it into 2 processors, then each one does 50, you've doubled the performance. You load it into 10, it's 10 times the performance. You can build pipeline stages over 100,000 stages deep, so then you've accelerated it 5 orders of magnitude. Well, the other thing is what we see with traditional von Neumann computers is they do add cores, not very many cores because they're difficult to program, but as they add them, they end up getting bigger and bigger to be more power efficient and to be faster. And so the result is in the NVIDIA Hopper, for example, you have 556 million transistors. In a Cornami core, you have 600,000, so you can do almost 1,000 Cornami cores in the same silicon area as you do one NVIDIA core. So with that, if you compare things, it says that you have the area to use 930 processor cores instead of 1, but the NVIDIA one, is in fact faster, and so they have an advantage, but if you use 930 of them, then you end up with a much higher performance in terms of tokens per transistor in this case, and so about a 235x advantage in terms of the performance. But what's even better is the power. With the power, the same silicon area then allows you 20 times less power, or 5% of the power, to achieve the same level of computation. And as we go on to future generations up through Feynman, those cores get bigger in order to produce more performance, and so they consume more power, as you see in the red line for the future NVIDIA roadmap, and in the blue line at the bottom, you actually get less power because you're shrinking feature sizes, and so it becomes more efficient. The last thing, of course, is you don't want to rewrite your software. So you can use the existing software because with Cornami, a large share of software is written to a standard interface. For fully homomorphic encryption, there are about 6 interfaces. There's PyTorch for large language model inferencing and other things, but all of the complex parallel computing and compilation goes on at the primitives underneath the application programming interface. You can, of course, have an SDK and optimize it further, but for most cases, existing software will run in accelerated form. So what's happened? For the last 6 months, we have been in production on the chips themselves, so we now have real data, and this is an example created by a group of banks that are looking at security for bank accounts. They have a benchmark they ran in 3.7 seconds on plain text. If you run it on just with hardware on a traditional computer, it takes about 24 hours. If you run it on accelerated hardware, 4 servers runs about the same speed on the encrypted data as you would run on the plain text data. So it makes fully homomorphic encryption practical, cost-effective, and running at a speed that solves most problems. And the cost, about 3 orders of magnitude less cost per FHE operation in the Cornami approach to architecture compared to an H100. So now, as we showed this to more and more people, and we've had dozens of people running applications, running benchmarks, every once in a while someone says, well, wait a minute, if you're running 1,000,000 times an Intel Xeon for fully homomorphic encryption, what if I don't need fully homomorphic encryption? What about without security? How does it perform? So we were finally forced into measuring that, and it turns out with around 20 concurrent users where we have benchmark data for the H100, we find a 10 to 20x advantage in tokens per second and a substantial power advantage as well. So it's a chip, 16 nanometer technology. It burns about 125 watts, substantially less than competitive approaches. And each core has precision that can be independently set anywhere from 1 bit up to 128 bits, double precision. So the compiler can configure the cores in such a way that data flows for the optimum precision through the system. So if you look at a 128,000 core server, we measure data here, about 20x in inferencing. If you want to do zero knowledge proofs for blockchain, about 17x compared to traditional computers. And remember, this scales up to tens of millions of cores. This is only 128,000 cores. There are 2,000 cores per chip. And it accelerates other applications very well. Now, for everything I've said here, I've been comparing a chip manufactured with 16 nanometer technology to the H100, which uses 4 nanometer technology, 3 generation nodes behind. In fact, more than 10 years old technology. What would happen if you just implemented this same technology for the Cornami architecture with 4 nanometer technology? It's a much better comparison to an H100, for example. And just to show you the end result, if you just look at Elon Musk's Colossus AI data center, which uses 25,000 H100 servers, it burns 150 megawatts. If you do that with the Cornami at 4 nanometers, what you will get is 28 Cornami fractal core servers, 3 racks. It burns 130 kilowatts, so 3 orders of magnitude improvement in power. So all of the warnings I hear about we can never generate enough power to power all the data centers, probably true if we don't innovate. But this is architecture alone produces 3 orders of magnitude. Surely there will be other innovators. So I think the fear of exceeding the power capacity of the world is very much overstated. So to summarize, real-time, fully homomorphic encryption, the holy grail of encryption, keeps the information encrypted at all times with a quantum proof or believed quantum proof form of encryption. Secure inferencing can protect the large language model. It can protect the user making queries. And the TrueStream architecture, the software that allows for the compilation into parallel streams, that also allows it to be linearly scalable. You don't have memory bottlenecks. You have no contention. It is a share-nothing architecture. Nothing is shared. All the memory operates independently per processor. You can do real-time, fully homomorphic encryption. You can run AI applications without modification and get approximately 20 times the tokens per second with the current technology at about 60% the power. Or if you do it at 4 nanometers, which we haven't done yet, that would provide about 900x performance with less than 1/4 of the power. So thank you very much. Are we okay? I can take questions. Any questions? Yes.
Before using fully homomorphic encryption, do you experimented with other privacy-enhancing technologies?
So the question is, hey, all this discussion is here about fully homomorphic encryption. What about other privacy-enhancing technologies? And the answer is no. We haven't dug into them because we sort of view that FHE is the ultimate in data security. If you can do that real-time and cost-effectively, why would you need a different one? But it's probably a worthwhile experiment. Anything else? Yes. Okay, when are we showing live demos and when can you buy one? The answer is we're building and testing servers now. We're in the 2nd generation of the chips, so the chips are fine, no problems. We expect to have beta units in customers during this quarter, and the target is to be taking orders and shipping volume in the 4th quarter or possibly September, one or the other. Good. Thanks very much.
Great, thank you so much. Thank you so much.